Chapter 3A.1 Neural Communication. For scientists, it is a happy fact of nature that the information system of humans and other animals operates similarly, so similarly in fact that you could not distinguish between small samples of brain tissue from a human and a monkey. This similarity allows researchers to study relatively simple animals, such as squids and sea slugs, to discover how our neural systems operate. It allows them to study other mammals' brains to understand the organization of our own. Cars differ, but all have engines, accelerators, steering wheels, and brakes. A Martian could study any one of them and grasp the operating principles. Likewise, human animals differ, yet their nervous systems operate similarly. Though the human brain is more complex than a rat's, both follow the same principles. Chapter 3A.1.1 Neurons. What are neurons and how do they transmit information? Our body's neural information system is complexity built from simplicity. Its building blocks are neurons or nerve cells. Sensory neurons carry messages from the body's tissues and sensory organs inward to the brain and spinal cord for processing. The brain and spinal cord then send instructions out to the body's tissues via the motor neurons. Between the sensory input and motor output, information is processed in the brain's internal communication system via its interneurons. Our complexity resides mostly in our interneuron systems. Our nervous system has a few million sensory neurons, a few million motor neurons, and billions of interneurons. All are variations on the same theme. Figure 3.2. Each consists of a cell body and its branching fibers. The bushy dendrite fibers receive information and conduct it toward the cell body. From there, the cell's axon passes the message along to other neurons or to muscles or glands. Axons speak, dendrites listen. Unlike the short dendrites, axons are sometimes very long, projecting several feet through the body. A motor neuron carrying orders to a leg muscle, for example, has a cell body and axon roughly on the scale of a basketball attached to a rope 4 miles long. Much as home electrical wire is insulated, so a layer of fatty tissue called the myelin sheath insulates the axons of some neurons and helps speed their impulses. As myelin is laid down up to about age 25, neural efficiency, judgment, and self-control grow. Fields, 2008. If the myelin sheath degenerates, multiple sclerosis results. Communication to muscles slows with eventual loss of muscle control. Depending on the type of fiber, a neural impulse travels at speeds ranging from a sluggish 2 miles per hour to a breakneck 200 or more miles per hour. But even this top speed is 3 million times slower than that of electricity through a wire. We measure brain activity in milliseconds, thousandths of a second, and computer activity in nanoseconds, billionths of a second. Thus, unlike the nearly instantaneous reactions of a high-speed computer, your reaction to a sudden event, such as a book slipping off your desk during class, may take a quarter second or more. Your brain is vastly more complex than a computer, but slower at executing simple responses. I sing the body electric, Walt Whitman said in Children of Adam, 1855. Neurons transmit messages when stimulated by signals from our senses or when triggered by chemical signals from neighboring neurons. At such times, a neuron fires an impulse called the action potential, a brief electrical charge that travels down its axon. Neurons, like batteries, generate electricity from chemical events. The chemistry to electricity process involves the exchange of ions, electrically charged atoms. The fluid interior of a resting axon has an excess of negatively charged ions, while the fluid outside the axon membrane has more positively charged ions. This positive outside, negative inside state is called the resting potential. Like a tightly guarded facility, the axon surface is very selective about what it allows in. We say the axon surface is selectively permeable. For example, a resting axon has gates that block positive sodium ions. When a neuron fires, however, the security parameters change. The first bit of the axon opens its gates, rather like sewer covers flipping open, and the positively charged sodium ions flood through the membrane. Figure 3.3. This depolarizes that section of the axon, causing the axon's next channel to open, and then the next, like dominoes falling, each one tripping the next. During a resting pause, the refractory period, the neuron pumps the positively charged sodium ions back outside. Then it can fire again. In myelinated neurons, as in Figure 3.2, the action potential speeds up by hopping from one myelin sausage to the next. The mind boggles when imagining this electrochemical process repeating up to 100 or even 1,000 times a second, but this is just the first of many astonishments. What one neuron tells another neuron is simply how much it is excited, Francis Crick said in The Astonishing Hypothesis, 1994. Each neuron is itself a miniature decision-making device performing complex calculations as it receives signals from hundreds, even thousands of other neurons. Most of these signals are excitatory, somewhat like pushing a neuron's accelerator. Others are inhibitory, more like pushing its brakes. If excitatory signals minus inhibitory signals exceed a minimum intensity, or threshold, the combined signals trigger an action potential. Think of it as a class vote. If the excitatory people with their hands up outvote the inhibitory people with their hands down, then the vote passes. The action potential then travels down the axon, which branches into junctions with hundreds or thousands of other neurons and with the body's muscles and glands. Increasing the level of stimulation above the threshold, however, will not increase the neural impulse's intensity. The neuron's reaction is an all or none response. Like guns, neurons either fire or they don't. How then do we detect the intensity of a stimulus? How do we distinguish a gentle touch from a big hug? A strong stimulus, a slap rather than a tap, can trigger more neurons to fire and to fire more often. But it does not affect the action potential's strength or speed. Squeezing a trigger harder won't make a bullet go faster.